tell you about an interdisciplinary project between biology and physics. What we're doing in our lab is using a new method of measuring cancer drug efficacy using mathematical models. And then we'll apply this new method in assessing the effectiveness of a nanomaterial drug delivery system. So first, how do you measure the drug efficacy of cancer drugs at the moment? So let's say you're a scientist and you have a drug that you're interested in and you want to know how well it works. The first thing you would do is you would test the drug in some cancer cells. So this picture here is an example of some cervical cancer cells that would be grown in the lab. But this is one of hundreds of different cancer cell lines that you could choose from. So you have your drug that you want to test in your cancer cell line. The next thing you would do is put your cancer cells into this plate and put the same number into each of the wells. Then you would apply a range of drug concentrations from each column. So each column will have a different concentration of drug. You wait a couple days for the drug to take its effect, and then you measure the number of cancer cells. And you would get a drug dose response curve like this. As you would expect, at low concentrations of your drug efficacy is going to be low. But as you increase the concentration of your drug, eventually you'll achieve an Emax, or the maximum effect of your drug. Unfortunately, most cancer drugs aren't 100% effective, and neither is this one. Here, the Emax is at 0.95, meaning the cancer drug is 95% effective. You would divide your Emax by 2, and where that is on the curve would be your IC50 value. This IC50 value is the current gold standard method of measuring drug efficacy. The lower the IC50 value of a drug, the more effective it is, because that means that you can use a low drug dose in patients. Ideally, we want a really powerful drug that works at low doses. So here's the equation for drug efficacy showing how Emax and IC50 determine it. Now, what's the problem with this current method? The issue is IC50 values are very inconsistent from study to study. They're hard to reproduce. So how can we know for sure the IC50 values of our drugs? Now this data was taken from a study that compared the IC50 values from 2 databases. The x-axis is from one database, the y-axis from the other databases. And the points are the IC50 values. You can see that for all these drugs, there are 15 drugs that are compared. There's no correlation or relationship or agreement between the IC50 values of the 2 databases. Only for one of the drugs, 17-AAG, do you see that there is some pattern of agreement? So we have this problem where IC50 values don't agree between 2 reputable databases of IC50. So what is causing this inconsistency in measurement? Well, it's possible because IC50 and Emax, or measures of drug efficacy, change depending on measurement time. As you increase the time in which the cancer cells are exposed to the drug efficacy is going to increase. Here, we illustrated how, as you increase the measurement time, your Emax will also increase, the maximum efficacy increases. But also that means that the IC50 will shift. Now, so you have this shifting IC50 value that's not stable over time. So now scientists are struggling with IC50, and it's hard for scientists to compare drugs to each other. Another problem is that IC50 values are used by doctors to determine drug doses in patients. So doctors are using these inconsistent measurements to prescribe drugs. So fortunately, we've come up with a solution where instead of taking one measurement of cancer efficacy at one measurement time, which again is inconsistent, what we're going to do is measure the drug efficacy by following the cancer growth over the course of 2 weeks. So we'll take a measurement every 2 days for 14 days. And so we'll be able to obtain this data of how cancer growth is affected by drug efficacy over the course of 2 weeks, and a mathematical model that will give us new measures of drug efficacy. So to recap the method, first we have to perform a biology experiment that measures the growth of cancer cells over time and treat it with a range of drug concentrations. Then we determine a mathematical model for cancer growth that accounts for this drug effect and fits the data from our biological experiments. Finally, we will obtain a new IC50 and Emax for the drugs tested in our experiments. This way, we can have a more effective way of measuring drug efficacy that is stable over measurement time. So this is the mathematical model that we chose for cancer growth. This is the logistic growth model. Here is the general equation for the logistic growth model. This model is used very often in population growth. And you can see here, this is a plot of the model that the x-axis is time. So we're going to be measuring the cancer growth over the course of 2 weeks here. And we're going to be measuring the population of the cancer cells as well. And the reason why we chose this model is because this is what cancer growth should look like. Cancer grows really rapidly at the beginning, and then as it runs out of space and nutrients, it's going to reach a carrying capacity, K. So this is represented here in the equation. So since we are taking into account drug efficacy, we modified the equation here to account for this drug efficacy variable. So now we have this logistic growth model for drug efficacy and cancer growth. So I wrote a program that solved this mathematical model for logistic growth with the modified drug effect. And I chose these values to input into the program. So A represents the growth rate. Now from cancer cell line to cell line, the growth rate is going to be different. Some cancer cells are going to grow at a higher rate, so their growth rate A is going to be higher. But I chose 0.8 for this purpose. And also the carrying capacity will depend on the environment in which the cancer cells are in. And then I chose IC50 and Emax values, again, measures of drug efficacy. Then I ran the program at 5 different drug concentrations. So you can see here that this model looks like what we would expect with cancer growth at different drug concentrations. When there's 0 drug, the cancer growth is going to be higher, but as you add more drug, it's going to get lower and lower. It's going to be affected, the drug is going to affect the growth rate. So now we have this model for cancer growth with drug. We wanted to know how well this would work in experiment. But since we don't have actual experimental data, we decided to simulate what that would look like. So in real life, cancer cells are not going to grow in this perfect curve. And also, it might not be perfectly, exactly our model either. So in order to simulate what the conditions would be like in a real biological experiment, we added noise to each of the data points on this graph to obtain this one. So here you have this data set that we would potentially be similar to what we would obtain in the lab, and it has some variation from the one before. So next, the reason we generated this noisy data in the first place is to see how well the program can fit our model through it, essentially. So if anyone has ever had experience with Excel, you have this data and you want to fit the best line through it, this is exactly the same thing. But instead of a line of best fit, we are doing the curve of best fit using our model. And we would get IC50 and Emax values from this noisy data. Now, just like we would with an experiment, we would obtain multiple values for each of our data points. So I ran the simulation 10 times and obtained a graph that looks like this. This is just an example of one data set, but I had 10 of these data sets. Each were a little bit different, and depending on how the program applied the noise. And then I obtained values for IC50 and Emax for this noisy data. And the purpose of doing this is to see how well can our program fit the IC50 and Emax, how well can it determine this drug efficacy measure.